there's a couple of tricks. One very important trick is that called variance reduction. So the idea here is that, if you're actually observing these trajectories, the raw reward is actually not that meaningful. So if all the rewards across this trajectory are positive, if most of the rewards that you obtain from the environment are positive, you're going to keep pushing up probabilities of all actions. And that's not going to be very meaningful for your policy. So instead of the raw reward, what's more important is that whether the current reward you're obtaining is higher or lower than what you normally expect to get. So that at least gives you a sense of whether your policy of this particular action is in a step in the right or wrong direction. So therefore, a very simple extension is to introduce a baseline function that kind of scales this reward by a particular baseline. So this baseline should probably track like something like the moving average of all the rewards. So that gives you, what these the normal expectation of rewards you should get is. And therefore you see, in future rewards, you want to compare whether these rewards are higher or lower than a baseline. And again, you can show that it provably reduces the variance of this estimator while also remaining an unbiased estimation of your gradient. So this variance reduction with a baseline is very important. And usually these baselines are very simple. Just, an exponential moving average of the rewards can give you a big boost in performance. But we can also do better than that. Instead of just keeping a exponential moving average, which seems very simplistic, what we can also do is, I want to push up the probability of an action at a particular state if this action is better than the expected value of what we should get from that state. So in this case, the expected value of what we should get from that state should remind you of one thing, which is actually the state value function. So we call the state value function exactly computes, given this particular state and following either a policy or an optimal policy, what is the expected long-term reward that this state should give me. And on the other hand, your Q function, which is your QSAs, that will tell you if I'm from a particular state and I take a particular action under a policy or under the optimal policy, what is the expected long-term reward I get. So in other words, this QSA minus V of S exactly tells us what is the difference between taking this action, the benefit of taking this action with respect to my long-term expected rewards. So then if QSA minus V of S is large, then I should be happy by taking this action A. Otherwise, if it's small or even negative, then we should be unhappy with this action. So using this, we actually get a better estimator, which is that I'm going to scale it not by the raw term, the raw reward, or even reward minus the baseline. I'm going to compute the expected utility of taking this particular action from my state. So that'll be my QSAs minus V of S as evaluated by the current policy pi. So this actually presents our next method, which is actually a combination of Tuesday's algorithm and today's algorithm. So on Tuesday, we know that at the start, you don't know these Qs and Vs. So and Tuesday we presented some methods to learn them. So we can use Q learning or any of these deep Q networks to actually learn these Qs and Vs. And the combination of these methods is actually called actor-critic methods. They combine policy gradients and Q learning. Why is that? They will train two things. So they'll train an actor. An actor will be the one that outputs a policy. So in this case, given a particular state, you're gonna maybe start sharing some layers, and you're gonna then branch out. On one side, you're going to predict a policy, which is a distribution over your possible actions to take. And at the same time, I'm also going to predict a value function, which is the value, my Q, of a particular state and a particular action. So again, you can, these are called actor-critic methods because the policy is the actor that tells you how I should act. And the critic is the value function, the critic, which is a Q function, is one that evaluates how good the states and actions currently are. So how would you train these jointly? So for the critic, the one that estimates the Q values, we've actually seen from Tuesday's lecture that we can actually train it using deep Q learning. So again, we derive these Bellman optimality equations. We know that the Qs at optimality should have this term, the Q learning target, and the output from the Q network being exactly the same. So if that happens to optimality, what I can then do is compute the difference and try to minimize that to 0. So that would be how you train your value function, your critic. And at the same time, you will also train your actor, which is the one that actually outputs the policy and tells you which actions to take. So what is the objective function for training the actor? Again, that would be the objective that we just derived, which is that the gradient of j theta, which is how good a particular policy is. You're going to take gradients with respect to theta, and that's equals to the advantage, which is how good this action was. And how good the action was is actually given by the critic. So you use a critic to at a given state compute what is the value of taking action at that state, and this value will be your long-term cumulative rewards as estimated by your Q values, and you will subtract the baseline value of that state, which is an average over all possible actions. So this difference will tell you the difference in expected rewards by taking this particular action, and you will try to scale that by the log probability of taking that action. So if this is high, you will push up the value of that action, and you will try to take it more in the future. And conversely, if this is small or negative, you would decrease the log probability of taking that action in the future. Cool. So these are called actor-critic methods. Combining critics that evaluate the state and action value functions with actors, which actually tell you what actions to take. And I guess most of the methods, I think nowadays, I think these actor-critic methods are very strong baselines for many reinforcement learning problems. They're also kind of these like go-to baselines if you have a discrete set of actions that you want to take. And again, you want to use some of the tricks we saw in the previous lecture, which is that you want to use sufficient exploration. So at the start, your policies are bad, so you want to do sufficient exploration so as to actually get trajectories with actions that give you high rewards. You also want to, as you're doing exploration, you want to keep an experience replay, which is to remember some of the sequences of states and actions that you've taken and store it. And when you're doing these gradient updates, in both for the critic and for the actor, you want to sample a batch from your experience replay. You want to shuffle it, you want to sample a random batch. So you're actually decorrelating these samples. And likewise, you want to use fixed targets. So again, you want to use W minus a previous set of parameters to give you your Q-learning target while updating W for your predictions. And then maybe after a few thousand epochs, you would replace your W minus with the current value of W. So this fixed targets prevents the issue of non-stationary targets. Awesome. So that is the main, at least from the algorithm side, those are the main, and these are the main introduction to the different types of algorithms used in reinforcement learning. So just to summarize real quick, we looked at value-based methods. So these value-based methods, we started by looking at these MDPs, which formalize the reinforcement learning problem. We looked at important values, our Qs and Vs, and we derived these Bellman optimality equations. And then we showed how to obtain the optimal values of Qs and Vs using value iteration, policy iteration, tabular Q-learning, and the extension to deep Q-learning. So the benefits here is that you're using the structure of MDPs, and therefore they're more sample efficient. But the main problem is that after learning these Qs and Vs, you then have to rederive a policy, which might be difficult if your actions are high dimensional and you can't really take argmax over your actions. On the other hand, in today's lecture, we've actually looked at more policy-based methods. So instead of using these value functions, your Qs and Vs, you will try to estimate your policy directly to just define a model that takes in states and predicts your actions. So that's your policy. And you will update this using a policy gradient method, which is the gradient estimation that we just looked. So the benefit here is that you're directly learning the policy. You don't have to go through all this trouble of learning your Qs and Vs and then deriving a policy. But the issue here is that because you're not really leveraging any structure in the problem in these MDPs, you are most likely going to be less sample efficient. And we also looked at how we can combine these methods using actor-critic approaches, where you have an actor that using policy gradients predicts a policy. And at the same time, we have a critic, which predicts these Q values that tells you, how good each of the actions you are taking are. So instead of, actually just using the rewards or rewards minus a baseline, you will use a critic to estimate how good these actions are. So that's kind of in the middle, these active critic methods. So now we're going to look at some applications. We'll look at two sets of applications. Last week, I just went very quickly using, I went very quickly through like language and reinforcement learning. Today, we're going to look at another set of applications which uses RL to do stochastic optimization. And this will be very useful in kind of optimizing over your discrete tokens, like you need to do in text generation. So we're going to look at stochastic optimization. So what is this area of stochastic optimization? So here's a very general optimization function. I'm going to take a max with respect to some parameters phi. And what am I going to take the max of? I'm going to take an expectation with respect to some distribution of z. And this distribution of z actually depends on phi. And once you're able to sample some values of z from this distribution of z, you're going to evaluate f of z, which actually tells you how good each of these z's are. So why did I give you this problem? Well, this is a very general problem setup that we actually saw before. We actually saw this in VAEs. So if you recall what we had in VAEs, we started by deriving this evidence lower bound, right? And in this case, the evidence lower bound depends on x and also depends on two parameters, theta and phi. So what are these two parameters? So again, given x, you actually have two sets of models, an inference model, Q of phi, that takes in x and predicts a distribution over z's. So x is your input data, z is your unobserved latent variables. The inference model takes in your observed input data x and outputs a distribution over z's, your q phi z given x. And then we saw that you have to sample a new set of z's before you can actually put it back into the generative model. So the generative model would take in z's and use a generator p with respect to theta, parameter theta, that actually takes in z's and outputs a distribution over your real data x. Right? This sort of was a VAE formulation that we looked at last Thursday. So we saw that the goal, which was to maximize this evidence lower bound, can be rewritten as an expectation under the inference model, the log likelihood of predicting your real data under the generative model, minus this KL term, which encourages the distribution of your latent variables to be close to your prior. So I'm going to ignore this KL term for now and just focus on this part, this optimization problem. So this and this actually share many similarities. So if you recall for VAEs, we know that the gradient with respect to theta is very easy to do, right? Once you have sample z, you're going to put parameters theta and predict your x and maybe define your log likelihood or your mean square error. And that is directly differentiable with respect to theta. So the generative model is very easy to learn. The difficulty was in learning the inference model. Why is that? Because in the inference model, you have an expectation under the inference model, expectation of under the samples from this inference model, and some term that further depends on z. And you want to be able to take gradients all the way back, all the way from the outputs of z through z and through the parameters of the inference model that generated this distribution over z. And why was that difficult? We saw that one option was to take in your inference model from x through parameters phi, get a distribution over z, and then sample z from this distribution, and then continue on with your computation. But once you start sampling z, the issue is that you have this this random sample that you can no longer backpropagate through to the parameters phi that output your distribution over z. Right? This is a stochastic bottleneck, this random node over here. So we saw how to kind of get around this problem by reparameterization. So instead of sampling z from the distribution as given by the inference model, what you should do instead is to just sample epsilon, a noise vector, and then do a linear transformation of this epsilon using the mean and variance parameters as given by q of z. So what you will get is that the randomness is now within this epsilon, and your z would now be deterministic. so that your z can actually go on to further computations to actually reconstruct x. And all these loss functions can now backpropagate with respect to z, which is deterministic, and backpropagate with respect to phi, which are the parameters that generated the mean and variance of your Q of z. Right. So all of this was back in the VAE lecture last Thursday. So we look at the similarities here. Again, theta was easy. The main similarities is in optimizing for phi. You actually do exactly get this formulation, right? You're taking an expectation under Q, which depends on phi, that actually defines the distribution over z, from which you have to do some sampling. And then the sampled z then goes through some computation. And that's why we call it stochastic optimization, because in this computation graph, there's a part where you actually have to sample certain layers or certain variables before these variables can then define your reward. That's why we call this stochastic optimization. So now that we've seen this general stochastic optimization problem encapsulates VAEs, and we saw that we saw that we can actually solve, at least in the VAE case, by reparameterization. But what are some requirements that we can actually get it to solve by reparameterization? There are a few. So we first have to require that z is continuous. Why is that? So once z is continuous, then you can actually go through computation afterwards to compute your loss function, and then compute the loss of your the gradient of your loss with respect to z, right? These gradients are only well defined if z is continuous. And in the case of VAEs, z is continuous because your Q of phi defined a Gaussian, and then z was a continuous sample from this Gaussian. So z is continuous. We have that in VAEs. What we also have is that Q of z is reparameterizable, and we saw that as well. We saw that instead of sampling z from the distribution as given by the latents, we could instead sample a noise vector from just standard Gaussian noise, and then obtain a deterministic z using a linear transformation of this noise. And this linear transformation would be by the mean and variance parameters as output by your inference model. So at least in the case of VAEs, our Q of z was reparameterizable. So we could move the randomness into epsilon and have z deterministic, and you could backpropagate gradients through z and to phi. Something else we needed was that f of z, which is all the computation function that goes on after z, that is also differentiable with respect to phi. And in the case of VAEs, we do, because once you sample a discrete z through reparameterization, it just goes through a bunch of neural network layers to get your output and define your loss. So all of this is also differentiable with respect to phi. So these are some requirements. And now let's look at reinforcement learning. So in reinforcement learning, we actually have a very, very similar setup, right? If you look at what we derived in the first half of the lecture, we looked at all this set of parameterized policies, with policies that take in states and go through some set of parameters phi to predict actions. And we looked at the expected reward of all these policies, right? That's a function of your parameters phi. And we saw how we could rewrite this as, again, a maximization problem of my policy parameters phi, an expectation of trajectories sampled from this set of from this particular policy, times an expectation of the reward of these trajectories, right? So this was the exact reinforcement learning problem that we had, which we then derived policy gradients. So what is happening here? So first observe that this and this is again under the same formulation, where you're maximizing over some parameters. You have an expectation in which you have to actually take samples from a distribution. That's why we call it stochastic optimization. And the distribution actually depends on the parameters phi. So again, the big issue here is that once you take samples from this distribution, and then your reward is only defined on these samples, how can you actually backpropagate this reward through your stochastic sampling process and with respect to phi? So what is different from reinforcement learning? Why can't we use reparameterization? So in RL, at least what we've seen for this set of discrete actions, instead of z being continuous, our trajectories are now a sequence of discrete actions. Given state, some set of discrete actions that you take. So we no longer have this this property where the things that you're sampling are continuous, which is kind of bad. Another big issue is, the probability of your trajectories given your current policy is also not reparameterizable. And that follows on the same argument that, now T is a set of discrete actions. So your P, which is basically your policy, that's going to output a multinomial over your possible actions. That is not reparameterizable like how Gaussians are. So that's also a big issue. And lastly, once you get your states, you're going to go through a policy to get actions. So a sequence of actions to your trajectory. When you go from trajectory to rewards, instead of having these decoder layers that you did in variational autoencoders, now you just have a black box function, right? Why is it a black box function? Because you have all these actions that your agent is taking. You're going to give it to the environment. This environment is a black box. We don't have a parameterized function for the environment that we can differentiate with respect to. And now this environment is just going to spit me out some reward. So this dotted line question mark here basically means that this reward is a black box function with respect to your actions. So then that gives you it's almost impossible to take gradients of your reward with respect to your actions or with respect to the policy parameters phi. So although both of these fall under the same framework of stochastic optimization, we've seen that there's some conditions that, if met, we can actually solve stochastic optimization through reparameterization. But at least in the case of RL, because of discreteness and because of this black box function that produces the rewards, we can no longer do this. And what we've actually seen reinforce our policy gradients is actually a very general purpose solution to solving for these stochastic optimization problems. So recall what we did in reinforce was that, given this problem, we want to take gradients with respect to phi. We show that a gradient with respect to phi can be written as something like this. This is the exact equation that we derived, which is an expectation under distributions from your Q, f of z, which is the reward of a particular trajectory, scaled by the gradient with respect to log probabilities of that sample. So that's exactly what we derived when we did policy gradients, right? We're gonna, take scale it by the rewards of a trajectory and the log probabilities of taking those actions, right? So in this case, our policies basically corresponds to this Q of phi. Our rewards correspond to our f of z, and you're maximizing over parameters phi, or in this case, theta. So reinforce, as what we've derived, is a very general way of taking gradients with respect to these stochastic optimization problems. And once you take gradient, you can actually compute a Monte Carlo estimate. So instead of taking true expectation over your Q of z's, which is difficult, what you can do is just sample a bunch of the z's. So sample a bunch, and for each of the z's, compute f of z, and then also evaluate the gradient with respect to the log probability of picking that particular z. And then I'm going to take an average over a bunch of z's. So by replacing the expectation with respect to an average. And that's exactly what we've seen, right? In this case, the z's are trajectories. I'm going to sample a bunch of trajectories. In this case, it's one sample, one trajectory, but to do an estimate, you would take a sample over a bunch of trajectories. And for each of these trajectories, you would compute the reward, which is your f of z's, and then a gradient of taking all of the actions in that trajectory. So the reinforced estimator, as we've derived, is a very general estimator for these stochastic optimization problems. And the good things are that, we just need a distribution Q to allow for easy sampling. As long as you can sample all these z's, you're good. So that means my z can be discrete or continuous, right? In our case, our z's, which is trajectories, they are actually, discrete actions being sampled at each time step. So z can be discrete or continuous. Q of z, which is the distribution the distribution over your z's, or in our case, the distribution over trajectories, can also be discrete or continuous. In our case, our Q of z was basically our policy pi, right? That, take in states and outputs a bunch of actions, a distribution over actions, but then you have to sample an action before you compute the reward of those actions, and therefore the reward of the trajectory. So the Q of z's can be both discrete and continuous. One thing that it must be is that it must be differentiable with respect to phi. So obviously in our case, our parameters, our policy is parameterized by theta, and you must be able to take gradients with respect to theta of the policy. So that is very easily achievable. But the good thing is that Q of z can be discrete or continuous. And the other good thing is that your f of z can be a black box, right? You no longer need something like a decoder that had gradients with respect to like in VAEs, but now your f of z's, or in our case, the reward of these trajectories, it can be just any arbitrary black box that you give it a trajectory and the environment would return you some reward. You just need to be able to query it. You don't need to know what's actually inside. It can just be a black box that you can query. So the reinforced estimator for stochastic optimization has all of these benefits. So we've seen these benefits in the case of reinforcement learning. We had some discreteness in our actions. We had this black box reward function given by the environment. But what are some other important applications of using reinforce? And that will be in text generation. So in text generation, if you want to define these generative models like GANs for text generation, one big issue is that text data is indeed discrete, right? So in this case, you have true data from the real world. So again, if you recall, GANs have this generator that generates text, and you also have a discriminator that takes in real text from the real world and the text that you generate, and you will try to distinguish between these, right? And then you would play a minimax game between the generator and the discriminator. So text data, both from the real world and also what you generate, they will be discrete. So you can think of, your generator will be some LSTM or transformer that outputs probabilities of words at each time step. And then you will need to sample these words to actually get a sentence. And once you get a sentence, you will compare it with some real sentence from real world data. And your discriminator will try to give you a signal of how close or how different these two sentences would be. So that's one main issue. And therefore, this discriminator gradient does not exist, because once you start sampling these words, you can no longer take gradient with respect to what you had before sampling. So how can you do this? So here, I think here's one of the early papers called sequence scan, which is a sequence generative adversarial networks. And what it did exactly was to build a generator and discriminator for text generation. So what the generator was given a particular words, maybe given 3 words generated so far, your generator would be some language model that would then define next words to generate. So the words to generate will be your next actions. And you will do some search. It's not really important what this search is, but you can just think of it as an efficient search strategy for the most likely sentence. Because if you want to generate a sentence of 10 words and you've generated 3 words so far, you actually have to possibly search over all vocabulary size to the power of 7 next words in order to get the true arc max of your sequence, right? So you can do some simple heuristics, like you can do local maximums at every time step, or you can do something in the middle, which is what they're doing, called a Monte Carlo search. But that's not super important. Just know that the generator will take in some words and it will try to predict the next words to generate, so that you can actually sample an entire sentence from the generator. So once you sample an entire sentence, you want to apply this discriminator on either real sentences or the sentences that you have generated. And if they're similar, so if what you generated is similar to real text, you should give a high reward to your generator, and otherwise you should give a low reward to your generator. So what would you do now? So again, it's not differentiable, but you can apply these policy gradient methods. So what you would do is you would sample your z1s to zk's. So what these are would be, each of these z's would be complete sentences as output by the generator that you have sampled from the generator. And the generator will define a distribution over your z's, right? So that will be your language model. And after you've sampled all of these complete sentences, what you would like to do is you would like to compute gradients with respect to phi, which are the parameters of your language model, your generator, of the expectation under the sampled sentences or a distribution of sentences, and the reward of each of these sentences. And we saw that using policy gradients, we could approximate it using a Monte Carlo sample. Sample a bunch of complete sentences. For each of these complete sentences, my reward will be given by the discriminator reward. So how close it is to real text. And you will multiply this by the gradients of the language model with respect to language model parameters, the likelihood of generating each of these sentences. So again, the intuition here is that for some of these generated sentences, they're going to look like garbage. So the discriminator reward is going to be very bad. And then you will want to decrease the log likelihood of generating those sentences of the language model, the generator. And for some of the generated sentences, at the start, just by luck, and eventually as you get a better generator, some of these generated sentences are going to look really good, like real sentences. So that will get high reward, and you will try to push up the probabilities of the generator language model generating those sentences in the future. So so that's the basic application in text generation. And of course, training a discriminator is easy, right? The discriminator, it takes in true data and real and fake data. It will just train a classifier. Everything is differentiable. It's easy. There's no stochastic optimization going on. And of course, there's that was in 2017, and subsequently people have proposed better methods to do this. And there's some issues that at least in this case, you need to wait for the generator to generate the entire sentence, which might be quite long, before you get a single reward, which really reminds you of this sparse reward problem in reinforcement learning. So what you can do is you can define better discriminators that instead of giving a single feedback after the entire sentence is generated, give partial feedback for prefixes that you're generating. So this subsequent paper defined a discriminator based on recurrent models that compare real prefixes at every time step generated by the model with real prefixes from real text. So now you get better dense rewards. So again, under this formulation, your samples instead of complete sentences will just be prefixes. Your generator that defines the distribution over the prefixes that you want to generate is again your language model, and you will estimate the gradients with respect to your language model using these Monte Carlo samples that for every prefix, the discriminator tells you how realistic it is, and you would try to weight up the samples of those that have high reward. Also some things, like using large batch sizes, again, reinforces large variance, and is in general not super sample efficient. So you have to use large batch sizes. You have to subtract your baselines to make the variance lower, and just look at the paper for other tricks that they used. There's also other approaches. If you want to do text generation without actually reinforcement learning, there's also some approaches. I'm not going into too much detail, but I'm linking some references. And just to also go over briefly, what are some other applications? You can also apply this in dialogue. So in dialogue, again, you have a model, Q of phi, that's your generator model for your dialogue across multiple utterances. And you will sample these dialogue. So each sample will be the input message, a bunch of responses across your dialogue. And your reward, just because we've looked at these approaches, you can basically define any black box reward function, right? So you're not limited to a discriminator. So any type of reward function, like this paper looked at a bunch of auxiliary rewards, like how easy it is to answer your utterances, information flow across the sentences, how meaningful it is, if you had human data, or you can even get humans to annotate all these black box reward functions, you can use it in place of f of z, right? So as long as any reward function that you can define on your samples, it can be a black box. You don't need to take gradients of it. You can define it here. And even for things like blue scores, again, it requires you to have sampled the text into raw text, into these discrete tokens, and you can kind of compare these sample text to your reference, and you can compute blue score, cider scores. All of these black box evaluation metrics can be used in place of f of z, right? And again, those are not differentiable using standard gradient methods. One is because of the sampling that you have to do to get the text, and also all these blue score things that match n-grams. Those are in general not smooth differentiable functions. So all these can be solved using your policy gradients. I just guess one last application, just another few minutes. This last application would be that in using hard attention. So I'm sure most of you have seen soft attention, right? Soft attention is basically outputting an attention map that has gone through a softmax, so its values between 0 and 1. Hard attention, on the other hand, would be a discrete latent variable that you would try to output a probability of it being 0 and probability of it being 1. And you actually want to sample a discrete gate, which is either 0 or 1. Again, once you have this sampling process in the middle of your model, you can no longer backpropagate through it. So you can again use policy gradient methods. So in this case, we're looking at multimodal learning. You have language, visual, acoustic coming in at every time step. You want to use an LSTM to combine all this information. And what we're defining here are these hard attention 0 or 1 gates that basically tells me whether the visual modality at this particular time step is going to be useful. If it is, I should assign it 1 and it will go through, and otherwise I should assign it 0. So this particular time step would have 0 for the visual modality. So again, because I have to define a model that outputs a distribution over 0 and 1 before actually sampling the values 0 and 1, this part here is going to involve a stochastic sample. So you can't backpropagate with respect to these parameters. But what I can do is, again, using these policy gradient methods, my z's here will be my hard attention scores, which are either 0 or 1. My q of z would be this controller, which actually defines the distribution over my zeros or ones. So this would take in the visual input and tell me whether this visual input looks like it's going to be useful or not useful. So it takes in the input and outputs, probability that it should be 0 and probability that it should be 1. And if I want to take gradients with respect to the parameters of this controller, what I need to do is also define a reward function. So for each of these hard attention scores, 0 or 1, I'm going to actually apply it to my data and train a model to tell me how well it's able to classify sentiment and emotions, or whatever task you want to complete. And this classification accuracy can be used as a reward function to tell me how informative, how good my 0 or 1 hard attention choices were. So at the start, my 0 and 1s were random. It's going to mask out important visual features, and it's going to let in useless visual features. So my classification accuracy is not going to be good. So the reward is going to be low, and I'm going to try to push down those probabilities given by the controller. And slowly as I get better, I'm going to be able to accurately mask out useless visual features and let in useful visual features. So now my accuracy is going to be higher, and I'm going to push up these probabilities that gave me this these 0 ones. So that's another example. And we find that in the case of sentiment and emotions, it actually rejects non-informative visual features and passes through smiles. And in the case of image captioning, we're given an image. Hard attention also looks at a bird. Correctly looks at a bird, and over a body of water, you look at water. Well, conversely, if you use soft attention, sometimes it looks at the bird, but other times it doesn't really look at anything. So that's it. Let me stop there. For language and RL, we talked about these different types of applications previously, but I think all of these are also quite simple. So I will just leave these slides online. But just to summarize real quick, we looked at 3 classes of RL methods: value-based, starting from MDP, solving for our Qs and Vs, using policy and value iteration or Q learning, and then going back to obtain a policy. We've also looked at policy-based methods that throw away these Qs and Vs and directly optimize for a policy. And there's some trade-offs between these 2 methods. So value-based methods are more sample efficient because they leverage the structure of the problem at the MDP. But there are disadvantages that you have to compute all these expectations and argmaxes over your actions, your states, your trajectories, which is difficult. Policy-based methods, they throw away your Qs and Vs, they throw away the trajectories. All they need is just, sampling your actions and getting the rewards. But the disadvantage here is that, since it's much more general and flexible, it doesn't really exploit the structure of the problem and therefore are more sample inefficient. We also looked at, certain types of combinations called actor-critic approaches that trains a policy, which is an actor, and also critic to evaluate how good the states and values that the policy actor is currently in. We looked at, more generally, going from policy gradients, a general form of stochastic optimization problem, which is useful for reinforcement learning with this black box reward functions, but also in general for like text generation, where you have to sample discrete tokens, which you cannot normally backpropagate through. So looking at text generation, due to discreteness, black box reward functions, such as blue scores or discriminators, you can also use that. And hard attention, so your samples being your attentions and your reward functions being how useful this attention, this gated input is to your prediction problem. And to summarize for like language and RL, we've also seen a bunch of applications. I think on Tuesday we talked about things like instruction following. We look at giving external rewards to your model, so that you can actually encourage the agent to do better than random exploring. And you can also look at some of these slides, which give you some language as domain knowledge, which kind of annotates text to describe certain objects in the RL environments, and also better ways of designing your policies to answer these to follow these instructions. But cool, that's all.